Now, dear students, next topic, that is equilibrium of a rigid body. A rigid body is said to be in mechanical equilibrium if its linear momentum as well as the angular momentum does not change with time. It implies that the linear momentum and angular momentum both remains constant, right? So in this particular case we can say the linear acceleration nor the angular acceleration is possessed by the body. Means linear acceleration and angular acceleration of the body, that is equal to 0. Now here see, if total force, or we can say the net force acting on the body, that is equal to 0, means the vector summation of each and every force acting on the body, that is equal to 0, then in that particular case we can say this thing, the body will not have linear acceleration. Now we know this thing, the net force F, that is equal to dp by dt. So if F equal to 0, dp by dt, that is equal to 0. So if differentiation of p with respect to time t is 0, means we can say this thing, linear momentum does not change with time. So in this particular case, if net force acting on the body, that is equal to 0, then we can say the body that is in translational equilibrium. The body is said to be in translational equilibrium. So we can say this thing, this equation A is the condition for the translational equilibrium of body. Now suppose the net torque or the total torque acting on the body, that is equal to 0. Then in that particular case, angular acceleration will be 0 and angular momentum, that will remain constant, means it does not change with time. So here, if net torque or total torque acting on the body, that is 0, means tau 1 plus tau 2 plus tau 3 up to tau n, that is equal to 0. So here tau 1 plus tau 2 up to tau n, that is equal to 0. Then we can write sigma I equal to 1 to n vector tau I, that is equal to 0. So in this particular case, we can say this thing, the angular acceleration of the body, that will be 0. Now tau, that is dl by dt again, so L remains constant. If this condition is satisfied, means equation B is satisfied, then body is said to be in rotational equilibrium. So equation B, that is the condition for the body to be in rotational equilibrium. Okay. Now this equation A and equation B suggest this thing. Here we can say, if total force or net force acting on the body is 0, it implies that the vector summation of all the forces, that is equal to 0, means the summation of the x component of all the forces, that is equal to 0, summation of y components of all the forces, that is 0, and summation of z component of all the forces, that is equal to 0. And equation B leads to this thing, when total torque or net torque acting on the body is 0, means summation of the x component of all the torque, that is equal to 0, summation of y component of all the torque, that is 0, and summation of z component of all the torque, that is equal to 0. Now here, if condition A and B both are satisfied, it implies that if body is simultaneously in translational as well as in rotational equilibrium, then we can say the body is in mechanical equilibrium. Okay. Now see here. If we think about the mechanical equilibrium, so if the body is fixed at this particular point, okay, and forces acting on the body are in the direction as shown in the figure, then in this particular case we can say the body that is in translational equilibrium, because here the body is fixed at this particular point. Now both the forces are in downward direction, but when the body is fixed, it can't be translated. Okay, so that is in translational equilibrium. Now under the effect of this force, the torque acts on the body, which will try to rotate the body in this direction. But the same torque, but in opposite direction, will be produced by this particular force. We try to rotate body in this direction. So both the torques produced here are equal in magnitude and opposite in direction. So net torque, that is also equal to 0. So body is in rotational equilibrium also. So we can say the body that is in mechanical equilibrium. Suppose here the body is fixed at this particular point, but the direction of these two forces are opposite. Then in this particular case, body will not be able to translate it because it is fixed at point. But the torque produced by both these forces will be equal in magnitude, but will be in the same direction. So there will be net torque acting on the body. Or in other words, we can say these two forces or couple of forces will give you the torque. Okay. So here body that will execute rotational motion. So we can say it is not in rotational equilibrium, but it is in translational equilibrium, because translational motion is not possible. See, suppose here body is not fixed at this point in this particular case. So if it is not fixed, then it will execute motion in downward direction. So translational motion is there, but torque is 0. So rotational motion is not there. So here, if body is not fixed, then we can say there is the rotational equilibrium. Clear? So here, if both the equilibriums are there, we can say body is in mechanical equilibrium. Clear to all of you?